we define ut acting on any function is a function on x to f of and we just double comment. So this is our finite algebra, and we found that x is t and this determines to prove we want to check when this that we had. So okay, so now so this is a conditional imply and which will determine the factor. Find it out, right? If you have t converts with that, then it will converts with this one in the entry, zero everywhere, and one at the ij place zeros everywhere. Then you get a condition, and all that will find it out. Okay, I will give an example. So I will give this as an assignment. Now you just use the matrix units and do that b of h xi eta. This is a rank one operator corresponding to en aj. I mean, you don't even need to work with matrix or something if you don't like it. You work with this kind of operators. Rank operators are this will give you a linear operator. This is a rank one. Rank one means the range will be one dimensional. C times eta. It will be range will be one dimensional. So it's rank one operators. Okay. So if it commutes with all of t, the center, if it some operator commutes, it should commute with rank one operators. I think maybe you would just use orthonormal basis instead of xi eta orthonormal basis. You will get some conditions, and okay. From that you can see that it should be one. I mean, it should be constant times one. So these are the only examples we know as factors. Okay. We want to find there are Next class, I will do tensor products. Actually, this will isomorphic to be of H, and this is also a factor. Is said to conjugacy class. Conjugacy class. Have any element G, then GT in, I will write it. There is an action of the group on itself, and the orbits of that action is what is called conjugacy classes. The group is ICC, that is classes other than the identity, other than, I mean, identity will be just one itself, other than identity is infinite, incardinality. Okay, so what does it mean? If you take a T in G, then you can define on S is equal to the result. So, so this two elements are equivalent. There exists a T, two elements, S and S prime in G are equivalent. If there exists a T in G such that T S T T S T inverse equal to T S prime. S1 S2 S. And the equal classes are called conjugacy classes. Okay. So those of when identity equivalence class corresponding to identity will be just single. So other than that, all the other conjugacy classes should be infinite. Okay. Yeah. 1, 2, 3. Can be such that all but definitely many which are only many, which is just union of Sn, right? Union of Sn means yes, it can permit some. Yeah, that's okay. Union of Sn. You can see that this has infinitely many conjugacy classes are infinite. If it some permute something here, then you can shift it by using it. If it does something within, it is within something, right? You can shift it, for example, and you can do it infinitely. You will get infinitely many permutations. Right? It's very clear for exercise. And okay, another thing is exercise. S infinity is group with infinitely conjugacy class. Very easy to see. Another example is Fn. This is what is called free group of n generators. This is just, I mean, print up relation. I mean, fully divide. You try to, you will get equivalence generated by that. There is no relation. It's called free. These are two examples for us. So let's make the proposition. Lambda g is a factor. If and only if g is ICC group. Okay. So one way, suppose G is ICC, then you want to prove that it's a factor. So to prove that it's a factor, you consider X in lambda G, intersection lambda G, omega, okay, which is the center. Something in the lambda G, it commutes everything, so it is in the commutator also. It's just the intersection of this. Okay. You want to prove it's a scalar. Okay. Scalar times identity. That's what you want. Okay. So X is in lambda G. So there exists a C from C G to C such that I mean, we don't even look at that. Let's see. We know what is that C. Okay. Let C equal to X times E1, right? It is that we have already seen. C has to be X times E1. Then X acting on E R S T E S equal to summation C of, I mean, C is a function in L2. Okay. So C of T U T yes. If you want, I mean, we saw this in the last class. This is satisfied. X acting on any ES looks like this. If you want, you write it as E of TH, if you want, E of TH, which is equal to TS, which is equal to C of T, okay? Which is same as, I mean, I better write like this. T E. I mean, X looks like C of T to S. I mean, we can say that X looks like this, C of T U T. But then this makes sense as the strong topology or norm topology. But when you act it PS, it looks like this. That's what I want to say. Okay. Okay. So What is that I want to say? Okay. So now I want to say, so x is in lambda g, so it looks like this. I want to use the condition that it is in lambda g commutant also. Lambda g commutant means it has to commute with all those UH. I mean, all those unitaries. Okay. So now USB, USB in lambda g. Okay, then we have US x, US x equal to x US, which I write it as US inverse equal to x. Okay. I mean, star or US inverse doesn't matter because it commutes with that. X commutes with this. So I want to use this relation to show that x is scalar. Now we just evaluate this. X, US, X, US inverse acting on E R. Okay. Should I take E1? Let me take E1. Okay. E1 times ER. I mean, you can take any two. I think it will follow from this itself. Okay. I think it will follow from this itself. Let's see. Otherwise, I will change. Okay. I think it will follow from this. I take E1, E1. Okay. Equal to, of course, X E1, E1, right? Will it follow from this? I think so. Let's see. Okay. Now this is equal to X. If otherwise I will change it. It's okay. Okay. Doesn't matter. So now this is equal to US inverse. For the change, I will just use it. Doesn't matter. And so that it will be US. I don't have to take an inverse. So now US looks like this. Okay, now this is equal to summation T in G, and this US inverse, I can bring it as US here. US inverse is same as US star. It's unitary. Okay, this is equal to summation. So I write it as, I will do it in that step. US inverse, I bring it here. So summation T in G, C of T, UT acting on E1 is ET. Okay, ET, right? Which is equal to UT US come here, so which is also ET. This is ES. Sorry, I have to apply US. No, US. I mean US ES summation CT. This is summation T in G, C of S, C of T, UT ES. US acting on E1 is ES, and this is ES. Okay. Now this is equal to summation T in G. What you get is US U, so ES, so which is C of T, UT acting on this EST, ES. Okay. But I am not getting it. So let's use general thing. Maybe I will apply first. Anyway, we want to use this for some R prime. Okay. R prime. We know that US inverse equal to X. So this is true for all R and R prime. Okay. Let's just apply. Now this is equal to so E of if SR prime. Okay. And here I will get apply US, I will get E of SR. Okay. Then I apply that X, which has another, sorry, this is SR, and I apply the T, right? ETSR equal to ESR, right? Now this is true, this is equal if and only if when, oh, T equal to 1. I'll directly write the whole thing. Summation over T in G, US acting on will be ESR. Okay, now I have a T here, so I will get a T here. Then I will get a S inverse there. S inverse TR. S inverse, yes, I can take this 1. Okay, now I take it as 1. So E S inverse TR, summation over P CT. Okay. CT, I will get. Okay. Times E R. So this is just R. I'm sorry to change so many times. I'm just taking this. This inner product with 1 and ER and E1 ER. Okay. Now this is with ER and this is true for all R. So only when R is equal to this will survive. Okay. There is no R there. Okay. So this is just equal to when R should be equal to ST inverse, right? I mean, R is equal to ST inverse R. So T should be equal to SR. This is true for T should be equal to SRS inverse, right? SRS inverse. So this is just CSRS inverse. I mean, this is just orthonormal basis. So it will survive only R is equal to this. So that should be R is equal to this. So T, the summation T, only one of them will survive, that is equal to this. And here, if you apply that, now on the other hand, X E1 ER, okay. Now that is equal to summation over T in G, CT, and X acting on that will be ET ER. So it only for R equal to T, this is, I mean, R equal to T, this will survive, and this is just equal to CR. Okay, so we get CSR S inverse equal to CR for all R in G, for all S in G. Okay, right? That's what we get. So this implies C is a function. C is on conjugacy classes. Okay, but the conjugacy classes are infinite. If it is constant on conjugacy classes, if you sum, it will be infinity, right? Because it's L2, if you are summing it. Conjugacy class, everything else is 0. So it is a scalar. So this only that, and X is X of ST, C of ST in, okay. I mean, C of ST equal to lambda times delta ST. So in all the conjugacy classes are infinite, and it is because it's in L2, it has to be 0. If it is non-zero, it is because it's in L2. Identity conjugate is when ST is inverse equal to identity, it takes a non-zero value, and that is lambda 10. So external. Suppose lambda is it's not easier. Then we want to prove it's a and F C, capital C, contained in G is a conjugacy, is a finite conjugacy class. Okay. Apart from identity, something which is not identity. Our bases will shift and they will all be different. Be reversed. Okay, inside that. Basically, it's inverse. Yes. Inverse equal to U. This implies U is the base. And it's not identity. So lambda G is not a factor. It not, you have to, it should have infinite conjugacy class. Okay. Now we want to discuss one more thing. We want to prove that this is not actually B of H. It doesn't look like B of H, right? For that, we have to So that's that. Because you have this all these UT which are linearly independent. And definitely many of them. Okay, so and this is a fine, I mean, this is but there is non given in but if you have any that matter. Sigma finite is something there is not yeah. You have a finite algebra and you have a positive linear functional on that. This we want trace of function. Okay. So this is the definition of trace state. This is a stronger condition. So we want a linear, weakly continuous positive linear function. He said weak. Faithful. You already defined, I think. Trace of x star x equals 0. And trace of x always. So we have defined. So when there exists, when such a that's way of saying phenomenon. So finite. How we define it. That will be it's correct. We already seen that on one, if you evaluate, you get the clearly it's clearly and and we'll check it. Okay. Now let's check it. So suppose traits of xy. So let x comma y in of g given by c and d. Okay? Functions. C and D functions from C and D. Let's just write what it is. XY stuff. We know what it is. We put it. Okay? Is a function in L2. Okay. Okay. Now x E1 E1, which is equal to summation CP XY. Sorry. Trace of XY equal to XY E1 E1, which is equal to summation we have already seen this. So I am XY E1. V C of S. I think so. This is what we got last time, no? C of S, D of T in TS inverse. We consider the product, no? X with C of S, DS inverse. We computed last time. Okay. So use the computation. Don't want to do it again. Huh? S inverse T, S inverse. C of T inverse S. C of, oh, no, I'm saying yes. Oh, sorry. Oh, this is, sorry, summation is T. Oh, sorry. I forgot the summation. Summation is T and C of T. T S inverse, S inverse T. T inverse. Ah, the summation. T inverse S. You're saying T inverse S. And okay. Okay. So now trace of XY equal summation. So XY is given summation over T S in G C star D whatever of S. Okay, E1 E1. Okay. XY is given by C star D, where C star D is this. Okay, that's C star D Fs E1 E1. Okay. So what do we get? C star D at E1 is equal to summation. This is the at S. Okay. That will be means theta d yes E1, right? US yes. US over summation over yes. But then only S equal to summation over n summation d of T S inverse S inverse. Okay, this is okay. And E is E1. But then one matters here. Sum is okay. T inverse, yes. Okay. No, no. In C and D, trace of Yx E1, sorry, T of Yx. Okay. Is equal to, I mean, which is just D of T, C of T inverse. Both D of T. I mean, G, T or some more, same thing. Because of the so trace is a tracial state. TR is a see this trace of be the one and the ijth place. Okay. Eij, okay, whose kth entry is equal to delta kl. Okay. No, not delta kl, delta ij, delta ij with kl. Sorry. Ijth place is 1. Huh? The Ij is fixed. Okay. Eij, kth element is 1 if it is kl, both are equal to k should be equal to I, j should be L should be equal to yeah. Delta ij, comma this tuple should be equal to this. Okay. Then Eij times Ejj, this is just a diagonal element, one at the jj element, is actually equal to Ej. You can multiply and find it out. Okay. It's just matrix multiplication. Also, Eij is also equal to, I don't need it. Okay. Okay. This implies trace of, and on the other hand, Ejj times Eij equals 0 if I not equal to j. Okay. If I not equal to j. In fact, Eij, sorry, in fact, this is true. Okay. These are what are called matrix. Eij EKL equal to E delta J comma K EIL. Okay, you can write this relation. Okay, EIJ EKL equal to delta JK EIL. So we equal the trace of I naught equals. And that is this. Okay, I mean EIJ can also verify which is equal to EJ. That's clear, no? I mean IJ is placed. Okay, so EIJ, which is the star. Okay, now this is equal to, by tracial condition, this is equal to trace of JI A of JI E of IJ, and this is equal to trace of EII EJJ. Okay, so trace of EII equal to trace of EJJ for all IJ. Okay, so this then lambda has to be 1 by n. Okay, so this says that, so now you do the same thing for B of H. Okay, let H be infinite dimension. Okay. Then let T EI N orthogonal basis. Okay. Then we have trace of and T of EM equal to X EM. Rank 1 projection EM times E acting on Z vector Z EM. Okay. This is the rank 1 operator. It's a projection when n equal to m. Then we'll do the same thing. E T E N equal to trace of T M E. Trace of EM equal to delta n and m times trace of T E N. Okay. This will imply that trace of 1 should be identity. It has to be 1, supposed to be 1. Okay. This will imply trace of identity is infinity. If you just sum it, which is nonsense. Okay. So there does not exist. All these things imply that homomorphism. Weakly again. So lambda g is infinite dimensional. It is contained in B of H. So it's an infinite dimensional factor which is perfect to B of H for any this. So is finite. Uh, non-unital isometry. Unitaries are also isometry, of course. So non-unitary isometry does not exist. Okay. Inside this. Suppose you start. Okay. No. So suppose. So notice we have an isometry one. P of n. So something called partial isometry. This is clear. But this is a projection you want to prove. Okay. I mean, this is just a projection. Let's say this way. No, you. I'm saying you start use one is good. I don't know. So what is that? Answer. This is not I want to pay notice. U is as a projection onto range of U. Okay. U is as a projection. So let range of U. Okay. See, if I come tree, then the range is closed. I think we have done this. That is clear. It preserves the norm. Something converges in the range. The image and the pre-image will converge because the norm is preserved, right? Something converges U and converges to U. The pre-image also will converge. I mean, it will be Cauchy. Something is Cauchy, then this is Cauchy, then that you can. I mean, we are working with space, okay? So, I mean, so range is closed. Okay. If H naught is a, so it's a range of U, it's closed. Okay. It's contained. Okay. So now we want to prove that U star is projection on. So suppose if we have a xi in H naught, okay, then xi is equal to U of eta or something, right? Because this is star z equal to u star u eta. So u star u is 1, so it's u eta which is equal to z. Okay. On the other hand, z is orthogonal to h naught, then u star z. Okay. U star has, I mean, inner product with any eta is equal to yeah. Z is orthogonal to h naught. Then we get u star z, u star z u eta. Huh? U star z u star eta. No, I don't want that. What do I want to prove? I want to prove that u star is a not. So if z is orthogonal to h naught, I have it is 0 for any system. Okay. So z is orthogonal to h naught. Okay. So that means it's okay. U star no, it's not okay. U star z u eta, and z is orthogonal to this, but this is z which is equal to u star eta. U star eta. Now u star and u eta. U star eta. First this will go, then this will go as u. So which is u. So this is equal to. Okay. So u star z is orthogonal to n eta. So u star is 0. This implies u star z equals 0. This is true for all eta. Okay. This is so this implies u star z is 0. This implies u star good. Z is in h naught per. That's definition. So this all these things imply that u star is a projection onto h naught. This is the property of this is what it projection onto h naught. Okay. So u star is a projection. So this implies 1 minus u star is also a projection. Okay. This is a separate thing. What we have done is a separate thing, true, independent of this proposition. If you have an isometry, this is true for even partial isometry. Okay. Partial isometry. If you have an isometry, then u star is a projection. So 1 plus u star is a projection. It's a projection not orthogonal h naught. Okay. So this implies projection is a positive. P square equal to P. P equal to P star equal to P. So projection. Okay. So this implies 1 minus u star is trace is positive linear functional. So trace of 1 minus u star, trace of 1 is equal to u star. Okay. Now this is spatial. So u star u. Okay. Now trace of u star is 1. 1 minus trace of 1 is equal to 1 minus 1 equal to 0. Okay. So trace of 1 minus u star is 0. So since trace is faithful means if you have a positive element, if trace of x is 0, then it is 0. This implies trace of 1 minus u star, I mean faithful 1 minus u star equals 0. U star is 1. So this is united. If it is an isometry, these conditions imply that it is actually united. So there is no, so if you have an isometry, it's a unitary. So there is no isometry which is not unitary. This is what is called finiteness property. These isometries are some sort of infiniteness. So why, if you want to see why, what is infinity? Abstractly. If we have a injective, I mean, if you have an injective which is to a subset of it, proper subset of it. A set S is finite, if S is infinite, if you have an injection from S, it defined on that, to a proper subset of S, right? That is what is infinity. Finite set, you cannot do it. So which is a one-one function, which is a injection, I mean, which is a one-one function from a set into it, properly into it, okay? So here you have a unit. Unit is like a, for you have injection. But that infiniteness. So this is what the finiteness property. So we will see more in the next class.